Welcome back to Calculus 1. In this lecture, we're going to introduce a very important theorem in calculus known as the mean value theorem. All right, so before we get started, the term mean, we're going to interpret that as meaning average. Some of the interpretations we'll get to, we're going to think of maybe an average rate of change compared to an instantaneous rate of change. So keep that in mind for what we're going through. All right, a starting place for the mean value theorem is we're going to think graphically. So let's say we have a graph of a function, and let's pick 2 points anywhere on that graph. Let's label them here with x coordinate A and then an x coordinate B. Now with those 2 points, or any 2 points, we can find a line that passes through them. That line, we're going to call that the secant line, as we introduced way back in the beginning of our course. And that requires only algebra to find the slope. The average slope between those 2 points, or the average rate of change of that function, we just calculate it from our familiar slope formula, change in y values divided by change in x values. And what we get here is f of b minus f of a divided by b minus a. And this is the slope of what we're calling the secant line. This is an average slope or average rate of change. All right. Now, what the mean value theorem states in its most basic form is that there is a point somewhere between A and B on this graph where the tangent line is parallel to this secant line. And you might recall from algebra, parallel lines have the same slope. All right, now how do we find that point where the tangent line is parallel to the secant line? Let's just move our secant line up in a parallel fashion until eventually the secant line becomes tangent to the curve. So slowly move your secant line up without rotating it, keeping the slope to be the same. And what you should find is the tangent line, where it has the same slope as our secant line, looks to be right about there. And what the mean value theorem says is that there is a point. Here we're labeling that point C, where the slope of the tangent line equals the slope of our secant line. All right, before we get to the formal statement of the mean value theorem, let's just keep in mind a few things. So the slope of the secant line, this is our change in y values over change in x values, rise over run, f of b minus f of a divided by b minus a. Now think back to when we introduced derivatives. We did so as a first way to answer, a way to find the slope of a tangent line. So think back to a question, what is a derivative? You could say a derivative is a slope of a tangent line. So we're going to say here f prime of c, that represents the slope of our tangent line that has the same slope or parallel slope to the secant line in our sketch. All right. Think back to algebra. As we mentioned earlier, when lines are parallel, they have the same slope. So we have our 2 expressions there, the slope of the secant line, slope of the tangent line. What the mean value theorem says is there's a point C for which these 2 slopes, the instantaneous rate of change equals the average rate of change. Or in other words, the slope of the tangent line equals the slope of the secant line. Let's get to the precise statement of the mean value theorem. And like most theorems in mathematics, there's some conditions that are satisfied for you to reach the conclusion. For the mean value theorem, the conditions here start by saying, let's assume we have a function that is continuous on the closed interval, a to b. And notice the notation for intervals there. A and b are both written with brackets. A and b are both included in that interval. The second condition is that function is also differentiable, which is the technical term in calculus for the function being smooth or having a derivative that exists everywhere. The second assumption is that it's differentiable on the open interval a to b. And notice now, in interval notation, A and B with brackets are now not included in that interval. If both those conditions are met, the function being continuous on a closed interval and differentiable on an open interval, the conclusion of the mean value theorem says is that there is a number C between A and B that exists, such that the slope of the tangent line, f prime of C, equals the slope of the secant line, f of B minus f of A, divided by B minus A. All right, this is again what we saw in a previous lecture. This is an example of what we're calling in mathematics an existence theorem. The mean value theorem tells you that something exists, this point C, but it doesn't necessarily tell you how to find that. All right, before we get to some examples, there's a really nice, interesting physical interpretation of the mean value theorem. To do this, we're going to recall that derivatives represent instantaneous rates of change as well. So think back to that question, what is a derivative? You could say a derivative is a slope of a tangent line, and you can also say a derivative is an instantaneous rate of change. To get a nice physical interpretation, let's think of our function f of x as representing position. So we would have the average rate of change of position, which we're calling speed, versus the instantaneous rate of change of position. That's what's defined as velocity. All right, so let's just keep in mind a simple example here to give a physical interpretation. Let's say you traveled 180 miles in 2 hours. Your average rate of change, or average speed, would then be 90 miles per hour. 180 miles divided by 2 hours. All right, now there's a few possibilities for traveling 180 miles in 2 hours. You could just travel at a constant 90 miles per hour for 2 hours. That would be how you cover 180 miles in 2 hours. Now, you can't actually do that. In other words, you can't just instantaneously get in your car and accelerate or get to 90 miles per hour. You start from rest, where your speed or velocity is 0, and you gradually increase your speed, accelerate up to a certain speed. Travel on highways, your speed could be 50, 60, 70 miles per hour, could be anywhere above or below that average speed, 90 miles per hour. Now, what the mean value theorem says is, since our average rate of change is 90 miles per hour, what the mean value theorem says is there must have been at least one time when our speedometer read 90 miles per hour. Either you're traveling 90 miles per hour for all 2 hours, or your speed or velocity is changing. There must have been at least one point in time where your instantaneous speed or velocity was 90 miles per hour. All right, let's take a look at our first example here. The mean value theorem, its main use in calculus is to get to some results on determining when a function is increasing or decreasing, which is going to be what follows in some upcoming lectures. Now, what we can do in the meantime is at least try to find this point C, where the slope of the tangent line equals the slope of the secant line. The questions typically take the form like we see here. We're going to find a number C that satisfies the conclusion of the mean value theorem for this function, x to the 3/2 plus x, on the interval from 0 to 4. Now, the conclusion of the mean value theorem, that was that f prime of C equals f of B minus f of A divided by B minus A. You can still see it in the upper left corner there of your physical interpretation of the mean value theorem. That is the conclusion. Our goal is to find this x value C that makes that conclusion true. Now, this all sounds maybe a little bit complicated, but we have an interval 0 to 4, and we can start calculating some of the things that go into that. All right, the first part is we want to calculate for that interval what the average slope is. That's the f of b minus f of a divided by b minus a. So this one's pretty straightforward. We have a given to us as 0 and b given as 4. All right, so you get 4 minus 0 in your denominator. In the numerator, you have f of 4 minus f of 0. And if you plug 4 and 0 in, 0 is considerably easier to plug into your f of x there. You end up with just 0. But be careful when plugging in 4. Split up the 4 raised to the 3/2 power. First do 4 to the 1/2 power. That's a square root of 4. And then you can cube that. And you should find that 4 to the 3/2 power comes out to 8. Notice in your function, there's also the plus x term. So you plug 4 in for that x as well. And you should find that you get as your function value when x is 4, 8 plus 4, so 12. If you simplify that average slope, you should get 12 over 4 or 3. All right, that's going to be the right-hand side of the conclusion of the mean value theorem. The left-hand side, that's the f prime of c. So we need to calculate a derivative here. For your function f of x, this only requires the basic power rule. So you can bring down your power 3/2, subtract 1 to get your new exponent of x as x to the positive 1/2, and then your derivative of x is 1. Now notice I rewrote that 3/2 x to the 1/2. I rewrote that instead of a 1/2 power as a square root. That's just going to probably make some of the algebra in solving for the value of c a little bit easier, since most students kind of have a little bit easier time manipulating square root expressions rather than things with fraction or rational exponents. All right, now this is f prime of x. The formal statement of the mean value theorem references some x value c. So if we were to plug c into that derivative, you just get 3/2 times the square root of c plus 1. The conclusion of the mean value theorem would say that slope for the tangent line, f prime of c, should equal the slope of our secant line. And we calculated a little bit earlier, the slope of our secant line came out to 3. So what we need to solve now is this equation, 3/2 times the square root of c plus 1 equals 3. And we end up solving that for c to satisfy the conclusion of the mean value theorem. At this point, we basically just have an algebra problem. Pause the video and give an attempt at solving this for c. Let's go through this example. First, you can isolate the square root expression with c, subtract 1 from each side. What I'd like to do is I always try to kind of get rid of fractions, isolate the square root expression. You can multiply both sides by 2 and then divide by 3. And if you simplify that, you should get the right-hand side now comes out to 4/3. And then your final step to solve that for c, think of how you would undo a square root. You would square both sides. And that's why I converted in the derivative x to the 1/2 into radical notation, square root of x. It's probably a lot easier to cancel a square root by squaring than it is for you to think, how would you cancel a 1/2 power? You still cancel it by squaring, but it's a little bit more recognizable when written with radicals. So from there, to solve for c, we square each side. And what we get is 4/3 squared, which comes out to 16/9. Now, part of the mean value theorem says that the value c that we find here has to be in the open interval from 0 to 4. And if you check, 16/9 certainly is between 0 and 4. So the conclusion of the mean value theorem leaves us to finding C as 16 over 9. That's the value of x for which the tangent line has the same slope as our secant line, 3.